Good evening, friends. This is Akil Madupalli. Now, I am explaining about the design principles of a cantilever retaining wall. This is the diagram of a cantilever retaining wall. You can see clearly that this is the toe, this is the heel, and this is the stem. All these things are combined called as a retaining wall. This retaining wall is supported at one side. It's like a beam which is supported. Which is fixed at one end. Then we will call as cantilever. Same design we are designing for the cantilever retaining wall. Okay. And this is the active pressure. Active pressure means this active pressure comes by the surcharge, and this is the effective depth. You know that the effective depth of basics of RCC, and this is the small d which comes under bottom of the toe to ground level, and this is the H1 which is represented as ground level to top of the stem, and this is capital H which refers to bottom of the toe to top of the stem, and the bottom part of the diagram is shear key, and the pressure, this is a passive pressure, this is active pressure, this is the passive pressure, and the pressure acting on the stem is Ka into WH square by 2. Okay, it will act at the distance of h by 3, small h by 3, and the thickness of the slab is t, and we are denoting the distance of shear key is means the height of the shear key small a, and the length of the toe is b. Here we have determined the value that Ka into WH square by 2. What is meant by Ka means it is 1 minus sin phi by 1 plus sin phi. The phi is nothing but the angle of internal friction. Okay, this comes under the angle of internal friction. All these things comes under the soil mechanics and foundations. Okay, that is based upon the soil. Depending upon the soil, angle of internal friction varies. Now, the first step of the design principles of cantilever retaining wall is dimensions of the retaining wall. What are the dimensions of the retaining wall is? First we should find the minimum depth of the foundation. It is denoted by the small d. We have seen in our diagram, previously we have seen in our diagram, this is a small d. Okay, now in the first step we are finding the small d. Finding the small d. Small d is equal to P by W into 1 minus sin phi by 1 plus sin phi whole square, where P is equal to safe bearing capacity of a soil, and W is equal to density of soil, and phi is equal to angle of internal friction or angle of repose. Previously I have told you phi is nothing but the angle of internal friction. By this we can complete the first step, and now second step, overall height of the retaining wall h In this diagram we can find that from here to here, this is the overall height of the retaining wall. Here h is equal to capital H is equal to small d plus h dash. Here we know that what we can represent the capital H. This is small d plus h dash. This is nothing but this formula, where h dash, previously I have told, the height of the retaining wall above the ground level, h dash. What is the depth of foundation? Okay, this is the in step 1, second step completed. In step 1, now we are going with third step, thickness of the base slab. What is meant by base slab? I have told previously, this is the thickness. This is the thickness. How much thickness we require as per our design procedure, that we should find. Here thickness is equal to h by 12. The thickness should be the h by 12. What is the capital H? Means from here to here is a capital H. That should be capital H by 12. This is the thickness. Again, come the fourth step, height of the stem. We should find the height of the stem. How much stem we should require? What is meant by stem? This is the stem. In this diagram, this comes under the stem. Okay, we should design the how much height of the stem. Okay, what is the height of the stem? Small h is equal to capital H minus t, small t. Okay, what is the capital H? This is the capital H. From here to here, the capital H minus this thickness. If you reduce this thickness from total height, the stem height will be obtained. You can easily find the stem height. Next, width of the base slab, B. B is equal to 0.5 h to 0.6 h without surcharge. B is equal to 0.7 h with surcharge. What is meant by surcharge? Surcharge is nothing but the soil weight, the amount of soil or any particle that requires. Actually, we will consider as soil. The surcharge means it's extra loading. Okay, that is a surcharge. For without surcharge, if you are designing without surcharge, if you are designing while designing, you are not considering any soil particles, all these things, means we can use this formula. B is equal to 0.5, these values 0.5 h to 0.6 h. If you are while designing only you are considering a surcharge, here some amount of surcharge is there, then you can take B is equal to 0.7 h with surcharge. Okay, now first step has completed. Now we are dealing the second step, design of stem. Now we are considering the stem design. This is the stem. Okay, actually we know this is the stem. How to design the stem? All this comes under this step. Okay, maximum bending moment of the bottom stem, okay, is equal to m is equal to bending moment is defined by m, moment is equal to Ka into WH square by 2 into h by 3. Okay, here we have written as moment is equal to Ka into WH cube by 6, or directly Ka means we know that 1 minus sin phi by 1 plus sin phi WH cube by 6. Here they are taking moment at bottom. Okay, at bottom means what are the reactions you are acting? Ka into this bottom. What is meant by Ka? You know that Ka formula, Ka into WH square by 2 into h by 3. This is the distance, height. Moment is equal to load into distance, Ka into h by 3. We have got this formula by this. Next, factor or ultimate moment is equal to, from is we know that mu is equal to 1.5 into m. Okay, moment. Okay. Now, effective depth required. How much depth we should require? As we have seen this diagram previously, I have explained it. This from here to here is the effective depth. These are all things, effective depth and the nominal cover and effective cover. These are all things we have learned previously in RCC-I, reinforced concrete structures 1 only. Okay. For these things, for slabs, one type of effective cover will be there, and for if this is the effective depth, listen, if this is the effective depth and this one will be this distance is there, no, this one will be effective cover. Okay, that effective covers will have different distance for each type. Slab having one type of difference, and column having one type of difference, beam having one type of distance you should make from the reinforcement. These all things. Now, effective depth required. Mu. What is meant by mu? Ultimate moment is equal to 0.138 FCK BD square. These are the formulas comes by IS. Okay, from this we are finding that D is equal to root of mu by 0.138 FCK B. What is meant by FCK? What is meant by FCK? This is the characteristic strength. This is the characteristic strength. Means for M15 concrete, the characteristic strength will be 15. Means FCK value will be 15 kilonewton per meter square. Okay, meter or mm, that all these things. 15 kilonewton per meter square or 15 kilonewton per mm square. For M20 concrete, 20, and M30 concrete, 30, M40 concrete, 40. This depends upon the characteristic strength. Okay, now we are finding the mu is equal to 0.87 Fy ASTD. What is meant by AST? Area of steel required. D means depth, bracket 1 minus Fy AST by FCK BD. Okay, AST means area of steel, Fy means yield strength, FCK means character strength, B means breadth, D means depth. This is the formula we have taken from the IS provisions. Okay. Assuming diameter of the bar, find out the spacing. Okay. Distribution steel. What is meant by distribution steel? The vertical members means the top layer members. If while designing slab there will be horizontal lines, first we will be placing the horizontal rods and we will place longitudinal rods, and we will tie these two rods. We will tie. We will make tie. These vertical members are called the distribution steel. Distribution members. That should be 0.12% of cross section. Okay. Now, next we will be going to the step 3. Step 3. Stability calculations. We should find in this step how much weight it can be stable, at what extent it can be stable. Our design, how much while designing you should design for stable also. Pressure distribution at the base to be computed, taking moments of all the forces about the heel point A. See, this is the diagram. We are taking about all the forces about heel point A. What is meant by heel? This is the heel, this is the toe. Basically, we know from our childhood, the heel will be long and the toe will be short. Okay. we are taking the moments of all the forces at A. Distance of point of application of resultant forces from small a, Z is equal to sigma m by sigma w. This is the formula. Eccentricity E is equal to Z minus B by 2. This eccentricity and this also comes under RCC-I. If you are thorough with RCC-I, you can learn easy what is meant by eccentricity, all these things. Okay. Condition of E is equal to E should be less than B by 6, or condition. Maximum and minimum pressure at base. Maximum and minimum pressure at base. We should find the maximum and minimum pressure. Sigma maximum or minimum is equal to sigma W by B bracket 1 plus or minus, this is sigma E by B. What is meant by sigma? It is nothing but the stress minimum or stress maximum. Means we know that we should find the stress also. Okay. Now step 4, design of heel slab. Find out maximum bending moment of a heel slab. Take moments of all forces at point B. Before that we have taken at point A. Now we are taking point B. Before that we have taken a point A. Now we are taking the point B. Find out maximum bending moment and ultimate or a factored moment. We can name the ultimate or a factored moment. Calculation, area of steel, spacing and distribution of steel. Here they are telling to find out the calculation of area of steel. How much area of steel we required for our design, and how much spacing of steel we should require, and how much distribution of steel. For main steel and distribution steel, how much it required, we are finding. Now we are going to the step 5, design of toe slab. Before that we have designed the heel slab. Now we are going to find toe slab. Before we have done for heel slab also, we find the maximum bending moment, taking moments, all these things. Same, calculate the maximum bending moment in the toe slab, taking moments of all forces about the point C. This is the point C. For heel slab, for toe slab, they have told that take the moments forces at point C. That's why we are taking the moment forces of point C. This is the point C. We will take all the moments which occurs, we take as a point C. Before that we have taken it point A. Now coming to the step, find out the factored moment. Okay, calculate the area of steel, spacing and distribution steel. We can find the ultimate. Factored moment is nothing but the ultimate, before I have told you. Now step 6, check safety against sliding. After designing these things, we should check the safety, whether it is sliding or non-sliding. Basing on the clay and basing on the force, it may slide, it may move just. Okay, that's why we should check. Total horizontal earth pressure, P is P, denoted by the P. P is equal to Ka into WH square by 2, capital H square by 2. You know that Ka. Before that we have told that Ka is equal to 1 minus sin phi by 1 plus sin phi. Now coefficient of friction, it is denoted by the mu. Okay. Factor of safety against sliding. We should use some factor of safety. Why you have taken that coefficient of friction mu? In this formula we are taking that mu value. Factor of safety is equal to mu into capital W by P. It should be greater than 1.5. If it is not satisfying, the shear key has to be provided. If it is not satisfying this condition, factor of safety is equal to mu into W by P into 1.5 and P is equal to K into WH square by 2. These all the things, if it is not satisfying, it should be less than 1.5, we should design for the shear key. Shear key has to be provided. If it is not satisfying, we should find the shear key. We should design the shear key. That's why we have before only, if it may slide or not slide, it may satisfy, it may not satisfy. Before only, if you keep how to design the shear key also, if it is not satisfying, directly you can go to shear key. If it is satisfying, we can stop here, and if it is not satisfying, we can go to the shear key. Design of shear key. Intensity of the passive pressure PP, small capital P by small p, suffix P, capital P, suffix by suffix P, small p. PP is equal to Kp into P. What is meant by passive earth pressure? Passive earth pressure means, if this is the active earth pressure acting by the surcharge, the opposite pressure which will be acted on the heel or the toe, all these things are the passive earth pressure. If active earth pressure, this will be acting this side, passive earth pressure will be acting this side. It may give stability for, okay. Now, where Kp, small kp, is coefficient of passive earth pressure, Kp is equal to 1 by Ka. If what is it, maybe 1 minus sin phi by 1 plus sin phi. If 1 by K is 1 plus sin phi by 1 minus sin phi, we know that the phi, angle of internal friction. If small a, depth of shear key, then total passive force is equal to, if the small a is the depth of shear key, then the total passive force is equal to PP into area. PP into area. It will act on the, PP will be acting on this area, the shear key area. Shear key area. PP into here. Here we have one PP into area. Factor of safety against sliding. So you should find the factor of safety. Mu into W plus PP by capital P. Okay. You know that coefficient. Previously we have told. Mu is equal to coefficient of friction. Okay. Now we have completed the 7th step. Then check for shear. We should find the, check the shear. Okay. V means net working shear force. Okay. Net means total working of shear force. V is equal to 1.5 sigma P minus mu into W. Factored or ultimate shear force equal to V suffix U is equal to 1.5 into V. Formula. This is the formula you should remember. Normal shear stress is equal to shear stress is equal to tau V is equal to VU by BD. Okay. 100 into AS by BD. This is the formula. You know that IS 456 table 19. From table 19 we have occurred this formula. Okay. Tau C is equal to permissible shear stress. Our condition is from IS code, tau C should be greater than tau V. Tau C should be greater than tau V. Okay. If we satisfy the condition 100%, okay, then design is safe. If you are not satisfied this condition, we are having some small mistakes in our design. Again, we can rectify the mistakes and we can design it so the safe. Okay. Thanking you for watching my video. If you are interested, you can subscribe my video. Akil Modupalli is my channel name. Okay, you can subscribe my channel in YouTube. Goodbye.